For decades, scientists' understanding of black holes has been based on the description from the theory of general relativity proposed by Albert Einstein. According to this theory, a black hole is formed when a massive star collapses. When a star collapses, it creates a singularity, where all of the star's mass and energy are compressed into an infinitely small point. However, a recent study reveals that black holes are becoming increasingly peculiar. When scientists first confirmed the existence of these colossal objects in the 1970s, we once thought they were inert, motionless corpses. After that, the renowned physicist Stephen Hawking discovered that black holes are not actually completely black. They in fact emit thermal radiation. And now, two physicists have discovered that these very black objects also exert a pressure on their surrounding environment. According to co-author Xavier Calmet, a physics professor at the University of Sussex, UK, the finding shows that even static, non-rotating black holes have both pressure and temperature. This is even more exciting because it was completely unexpected. Calmet and his research fellow, Fogert Coopers, are studying the quantum effects occurring near a black hole's event horizon, an object of extreme difficulty to define. To address this issue, the researchers employed a technique to simplify the calculations. While working, they discovered a strange mathematical term in their solution. After months of pondering and research, they finally deciphered the meaning of this newly discovered term. It is an expression of the pressure generated by a black hole. No one could have imagined this was possible before. It was this very discovery that completely changed how scientists think about black holes and their relationship with the rest of the universe. In the 1970s, Hawking was one of the pioneering physicists in applying quantum mechanics to study phenomena at the event horizon, the region of space around a black hole from which nothing, not even light, can escape. Prior to the publication of this research, the scientific community had always conceived of black holes as simple entities. According to general relativity, the first gravitational theory to predict the existence of black holes, the event horizon is not particularly remarkable. The event horizon is the boundary surrounding a black hole. To escape this area, one must travel faster than the speed of light. S merely an imaginary boundary in space, for you wouldn't even realize you. Hawking was the one who completely changed everything. He realized that quantum foam, often likened to a sea of particles continuously appearing and disappearing in spacetime, could alter the conventional simplistic understanding of the event horizon. Sometimes, pairs of particles can spontaneously emerge from the vacuum of spacetime, then annihilate each other in a potential, returning the vacuum to its original state. But when this phenomenon occurs too close to a black hole, one pair may become trapped behind the event horizon, while the other escapes. According to the mass-energy equivalence principle, the mass and energy of an object are equivalent and can be converted into one another. When a particle escapes a black hole, it carries away a portion of energy. This energy is extracted from the black hole, causing its mass to diminish by a corresponding amount. This process is now known as Hawking radiation. And through these calculations, scientists discovered that black holes are not perfectly black. They emit a soft, faint light. This glow is called black body radiation, meaning it also carries heat and entropy. Hawking focused his research on how quantum mechanics affects the vicinity of a black hole. But the story doesn't end there. Quantum mechanics does not encompass gravity and also does not fully describe the phenomena that occur in the vicinity of an event horizon. It must encompass quantum gravity or describe the nature of gravity at an extremely small microscopic scale. Since the 1970s, many other physicists have also embarked on the quest to construct a theory of quantum gravity and applying those theories to physics research at the event horizon. The latest impetus stems from recent research by two scientists, Calmet and Coopers. Calmet stated that Hawking's groundbreaking breakthrough revealed that black holes are not actually black. However, its radiation spectrum closely resembles that of a black body. This makes black holes an ideal laboratory for studying the interplay between quantum mechanics, gravity, and thermodynamics. Currently, there is no complete theory of quantum gravity. Two scientists used a recent approximation technique called effective field theory, or EFT. This theory posits that at the quantum level, gravity is an extremely weak force. An assumption allows you to make some headway in a calculation without everything getting tangled up. This occurs when gravity is modeled in quantum mechanics as an extremely powerful force. While these calculations cannot paint the full picture at the event horizon, but they can provide deeper insights into the region of space surrounding and within the black hole. Can Met explain? If we only consider black holes within the framework of general relativity, it can be proven that they have a singularity at the center, a place where all the physical laws we have ever known cease to apply. It is hoped that when quantum field theory is combined with general relativity, we can find a new way to describe black holes. Met and Coopers are researching the thermodynamics of black holes by using effective field theory, EFT, in the vicinity of the event horizon. And they noticed a strange mathematical term appearing in their equation. Initially, the term left them utterly perplexed. They didn't understand its meaning, nor did they know how to explain it. But then, both scientists realized one thing. The term in this equation represents a pressure, a real quantity with actual physical pressure characteristics. The most memorable moment was when we suddenly realized that the mysterious answer from the equations we had created was the very solution to that question. The black hole we studied has internal pressure. After months of struggling with it, we felt incredibly excited. That pressure is almost unbelievably small, being only 1/10 carat 54 times that of the standard atmospheric pressure on Earth. But it's still there. They also discovered that pressure can be positive or negative, depending on the specific mixing ratio of the quantum particles around the black hole. Positive pressure is the type of pressure that helps keep the balloon inflated. Meanwhile, negative pressure is the tension you can feel in a rubber band when it's stretched. Their research findings reinforced the view that black holes are thermodynamic entities. Not only temperature and entropy, but pressure is also an important factor. Because their work only models quantum gravity within the realm of weak interactions and neglects strong interactions. Therefore, although it cannot fully explain the behavior of black holes, this remains a significant step forward. It can be concluded that our work is a step forward in this direction. And even though the pressure generated by the black hole we studied is incredibly minuscule, but in reality, it already exists and will open up countless new possibilities, encompassing the fields of astrophysics, particle physics, and quantum physics. And as our understanding of black holes deepens,